Hey guys, I have a rather quick video for you guys today where I'm going to be proving geometrically the fundamental theorem of calculus, which has two parts, and it states the connection between derivatives and integrals, which is huge because now the two kind of main branches of calculus, integral and differentiable calculus, now have a bridge that connects them through this fundamental theorem, which states that if you take the derivative with respect to x of the integral from a to x of f of t times dt, you'll get f of x. And it basically tells you that the derivative operator and the integral operator kind of cancel each other out and they're opposites. And the other thing that states is that if you take the integral from a to b of f of x dx, this equals the antiderivative of f of x, and we'll get to that in a second, evaluated at b minus the antiderivative of f evaluated at a. And these are the two parts, and this is the fundamental theorem of calculus. So it tells us the connection between derivatives and integrals in the first part, and it also tells us how to evaluate definite integrals in the second part. And to derive this, I'm going to draw an arbitrary function and ask us questions about the area under that function. So we know that the integral from a to x of f of t dt is given by the area under the curve f of x from a to x. So this area that I'm coloring in here represents the integral from a to x of f of t dt. And if you guys are familiar with integral calculus, you'll realize and you'll know that the variable of integration that we're integrating with respect to doesn't matter, because we call it a dummy variable, because it doesn't matter what we integrate with respect to as long as the two variables are the same. So the derivative from a to x of f of t dt is the same as the derivative from a to x of f of b db. It doesn't matter what variable we integrate to as long as they remain the same. So this area is the integral from a to x by definition of f of t dt. And we don't really know a lot about this function right now. We don't know how to calculate its value. We don't know how to do anything with it, but we can try and maybe find some properties of it. The first question that you might ask is, well, can we find the derivative of this function? And to do that, we'll say, okay, well, what happens if we nudge our input by some tiny value dx? What is the corresponding change in area, which we'll call dA, all right? And because dx is getting really, really small, our tiny change in area, if we zoom in, because of the property of local linearity, which states that as you get really, really small, curves become lines, the tiny change in area will be, and my drawing is awful, excuse me, will be dx times the function value at that point, which gives us this rectangle, plus some triangle at the top. And it is a triangle because, as we said, as we get infinitely small, the curve becomes a line. And what the area of this triangle is dx times dy times 1/2, just by the definition of a triangle, because this is dx, this is the tiny change in y, and times 1/2 gives us the area of the triangle. But we know that the slope of this line, because it's a line at this point and we're getting infinitely small, so it's locally linear, the slope dy over dx equals the derivative at that point. So by multiplying both sides by dx, I'm going to say that dy equals f prime of x times dx. So I'm going to substitute dy for this in our above equation, and you'll see why that's going to become, that's not the undo function. You'll see why it's going to become relevant in just a second. So the area of the triangle is actually dx times f prime of x times dx times 1/2. And then if this ends up being f prime of x, or 1/2 f prime of x dx squared. So dA, our tiny change in area, is equal to f of x times dx plus 1/2 f prime of x dx squared. Now, if we divide both sides by dx, we get dA over dx equals f of x plus 1/2 f prime of x dx. And because dx is going to 0, we can get rid of this term and ignore it. And we get dA over dx equals f of x. And notice what dA over dx means. It means a tiny change in area with respect to x gives this. What is a tiny change in area with respect to x? It's obviously the derivative of our area function, which will denote capital F of x, equals the function that bounds it. So that's the first part of the fundamental theorem of calculus right there. And I'll explain why in just a second. It tells us that if we have a function, f of x, and some area function that tells us the area underneath that curve, the derivative of the area function at any point is equal to the function value at that point. And that is huge, because what it tells us is that if we want to find a function for the area under the curve, we're asking ourselves, well, what function, f of x, has a derivative of f of x? And this is called finding the antiderivative of f of x, asking what function has a derivative of f of x. And what you'll end up getting is you'll end up getting some function that when you differentiate it becomes f of x, and then you'll end up adding c at the end. And the reason we add c is because when we differentiate a constant, it goes away. So when we find the antiderivative of a function, we have to add a c to the end of it, because it could be any family of functions horizontally translated that could be the antiderivative of that function, because as we said, when we integrate a constant, it goes away. So an example of this is we want to find the antiderivative of x squared. It's going to be x cubed over 3 plus c. Because when we differentiate it, we're going to end up getting this differentiated. 3 goes down, cancels with this, is x squared. And then c differentiated is 0. So this is x squared. So the integral of x squared is x cubed over 3 plus c, because the c, when you differentiate it, it goes away. So we can't ignore that, because technically the answer is any function with this property, with any value of c. So that's an important property. So if we go back to our original point here, it tells us that the derivative of the integral function is equal to the function. And that's literally what we just proved. It says the derivative of the area from a to x under f of x is equal to f of x, which is what we just proved. And then the next question tells us that we want to find the area under the curve of f of x from a to b. We take the antiderivative of b and subtract the antiderivative of a. Now, why can we do this? All right. So if we want to find the area between a and b, obviously what we're doing is we're finding the area under the curve evaluated at b and subtracting the area under the curve evaluated at a. So what that gives us is it's like this area is like from to b, and then this area is the a1. If you subtract b minus a, you get just this area, and that's what we're looking for. So what this ends up being is f of b minus f of a, by definition. So there's really nothing to prove here. It just tells us the integral from a to b, the area under the curve of f of x dx from a to b, is the antiderivative of b minus the antiderivative of a. And we just derived why that's true. And the fundamental theorem of calculus tells us that the area function is the antiderivative of x, or f of x. So if we want to find the area between 2 points, we just evaluate the antiderivative at those 2 points. Now, if you're paying attention, you might realize, well, Dylan, there's something important we forgot. Remember our antiderivative example of x squared? We said that the antiderivative is x cubed over 3 plus c. So how can we find a definitive answer if there's a c here? Well, then let's think of an example. If we're evaluating f of b minus f of a, we're going to get we're going to get b cubed over 3 plus c minus a cubed over 3 plus c. And you'll notice there's a plus c here, and then this negative gets distributed to a minus c. The c's go away. The c's cancel, so we're left with a definitive answer for the area under a curve. And that is why the second part of the fundamental theorem of calculus is so vital. We can bypass this little quirk here where we kind of said that okay, well, the antiderivative of any function can be any function that has this property, and C can be anything. We can bypass that by taking the antiderivative evaluated at one point, subtracted by the antiderivative evaluated at another point, and the C's will cancel, and you're left with the area between those 2 points. So that is the fundamental theorem of calculus, arguably the most important thing in calculus because it is a bridge between the 2 main segments of calculus, as I said. I hope that was helpful, and I'll see you guys in another video.